Welcome to a beginner-friendly tutorial on MLIR. So the reason this tutorial exists is because many other tutorials that exist for MLIR focus on the perspective of MLIR from a compiler engineering perspective, which is I want to build dialects. I want to build the compiler. I want to build the compiler passes. And that's really in-depth knowledge, and it gets kind of confusing to new people trying to just use MLIR for their different compiler applications. I would like to show a more beginner-friendly approach where we're not touching any aspects of the MLIR infrastructure. We're not writing any dialect code. We're not writing any pass code. What we're doing is we're just going to use whatever's built into MLIR to manipulate some code. And I wanted to show you guys how to do that. So in what I've created is this GitHub repository, which contains all the demos that I'm going to be talking about today. And each of these demos will walk you through a different aspect of MLIR that I think is very interesting. So the first demo will be a motivational demo. There's no MLIR in this. We're just going to motivate why we want to use MLIR. The next demo will talk about how do we take this motivational example, which I wrote in C++, how did I get that into MLIR? The next one will be talking about how to lower the code that we just brought in all the way down to a lower level of abstraction in MLIR. And finally, while we're lowering, what can we do? What kind of optimizations can we perform? And I'm going to provide an example through the affine dialect. So before we get started, if you want to follow along with me, I recommend going through demo 0, which is about building MLIR. What I've done is actually included LLVM as a submodule into this repository. So if you ever want to do these examples at any other point, they will always be exactly the same. And you can build MLIR using this command right here. It's just a CMake command that will do everything. This right here will actually build MLIR and check that everything's working as expected. That one line can take like 30 minutes to an hour, so give it as many cores as you can. But once you've completed these steps, and I go to my build folder, what you should find, let me just put this here, is a bin folder, which will have all of these executables. The one that we'll be working with today, or two, is MLIR OPT. And if we have time, we'll also be talking a little bit about MLIR translate, which is right here. All the other tools we can kind of ignore for now. Okay, so assuming we've built this tool, let's go through this example. So the first thing I wanted to talk about is why do we use MLIR? And to motivate this, I wanted to provide an example. So in demo 1, you'll find 3 files. I'm going to go here first. What I've created here is a very basic application that's going to be performing a fully connected layer. And the way I wanted to write this from a user perspective is I want to write this at the highest level as I possibly can. Well, to make a fully connected layer, all you need to do is take a matrix multiply between your input matrix and your weight matrix, which will create your output layer. So just to make this a little bit more clear, the input is usually a vector. In this case, it's a vector of length 512, but oftentimes in DNNs we batch. So this is a batch size of 256. So my fully connected layer, batch size 256, vector input 512. I pass this into my layer, which has maybe 1,024 hidden dimensions, and we multiply it by this matrix, and then we do an activation function. In this case, I'm choosing to use ReLU. So my goal here is the user has no care for how this is actually going to get turned into assembly language. What they want is to just perform a matrix multiply and a ReLU. So what I've done is I've created a library, which which has its own tensor abstraction. Basically, how will the memory be allocated on the CPU or on whatever device we're going towards, and linalg lib, which will have some linear algebra operations. The idea is very skilled engineers are going to be building this library for extremely high performance for their application. Imagine BLAS, imagine any of those libraries. And at a high level, our user just wants to do this. Now, I want to be kind of clear here. Usually, you wouldn't use C++ for this style of coding. There are libraries like this, but for MLIR in particular, this style of coding is mainly coming from Python. Something like PyTorch or TensorFlow. The user would write it at some high level, and then there are these excellent libraries in the back end that will just plug in and it will run super duper fast, hopefully. I do want to take a look at what these libraries are doing, though, before we go any deeper. So tensor.h is your memory abstraction. From a high level, all we really need from the user's perspective, they don't care how this is allocated, when it's copied. What they care about is just that there's a hunk of data going from this point to another point. But in the library, we have to actually turn this into a real allocation. And in this case, what I have to do is turn it into a vector, which will actually allocate a pointer and do everything it needs to do on a CPU. Now, if this wasn't a CPU and this was something else, maybe this would be a little different. And also, maybe you want to do some optimizations with how copies are performed with this particular data type. But the idea is that from a user's perspective, we don't care about the allocation, but from a library perspective, we do care about the allocation. Going to the library as well, what I've done is created very crude and simple implementations of matrix multiply and a ReLU. And in here, you're going to find a bunch of comments that I put in here. Now, if this was a real library, this is going to be hyper optimized. You would find that these loops would be probably turned into inline assembly. You'd find crazy optimizations. And I list some of the optimizations here. For example, tiling, hacking, vectorization, and maybe even using architecture-specific instructions. For example, this is a multiplication and accumulate. Maybe your architecture actually has a multiply accumulate operation. Or maybe even you have some kind of hardware accelerator that can perform matrix multiply right there. And then we need to tile it into the correct size and shape, maybe do some padding and stuff like that. But the idea is that the users of this library aren't aware of this, but the creators of the library, for every single compute or every single device that's going to be using this library, they need to make hand-tuned kernels for each of them. And the thing is, that's really expensive, if you imagine that. Every single time a new chip comes out and you want this library to be used by your users, you have to make these kernels or tune them up in a way that'll be optimal for your particular architecture. This creates a huge barrier to entry for new chips and new designs, and also it's a royal pain to work with because actually doing this is kind of tricky at times. So at a high level, what we have in this example is that our user wants to get huge performance gains, and they want to write code at this high level. It's really portable, it's really easy to use, and the user just does not care. And then our performance engineers, the people who make the chip mainly, are going to be making these high performance libraries that are going to be able to handle making this run really, really fast, regardless of which architecture you're using. So this is kind of what MLIR tries to fix. Because here's the problem. Making a new library for every single architecture you're ever going to hit is really challenging. And also, there are other problems with this approach in that we have to do all these optimizations. But for each architecture, if you're a CPU, tiling is always a good idea. The only thing that changes is the tile size, which it depends on the size of your cache. So it would be nice if there was some way of streamlining this process. Now, there are graph level schedulers which exist, like scheduling libraries. I forget some of the names, but I have them in my write-up on the main page of the GitHub. But there are some actually it's right there. So there are some libraries like Halide or TVM, which allows you to separate the optimizations from the kernels. So you can just tell it, I want to tile these loops by this tile size, and it will tile it for you. But they're kind of hard to work with, and they don't obtain the best performance that a compiler engineer could potentially give. The real problem here is that I have to write this at a pretty low level representation. Eventually, this has to get turned into a compiler where it has to get turned into instructions like add, subtract, load, store, branch instructions, which is a very low level representation. What would be nice is if the compiler can get more information. If you told the compiler, here's some high level information about the problem, you figure it out. You do whatever optimizations you need to make it run as fast as possible using that high level information, and the compiler brings it down to a lower level of abstraction and then does the rest of the compilation flow. So this is my motivational example, and this is where MLIR comes in. The idea is that if I can have the compiler at a higher level of abstraction, I can do better optimizations, like some of these amazing ones like vectorization, packing, and tiling, or you can do them more easily because the current compilers really struggle with like some of these. Is this motivational example clear to people? Sweet. So that was our motivation. And now what I have to do is I want to now enter MLIR. So I have this kernel, which the user wrote. This is at an entry level where what I want my user to be writing to me. And I want to turn this into MLIR. Now I purposely picked the API for this library so that it matches the MLIR dialects in the core dialect of MLIR. I chose that on purpose. Normally, you'd do the opposite. Normally, you would build a dialect in MLIR that matches your API. But I'm lazy, and I didn't want to have to write a custom tool for this. Now, if I look at this code right here, what I've done is I actually by hand wrote the MLIR code for this. And I'm going to walk through what this looks like. But if you kind of look at this quickly, you're going to see that it looks very similar to the above one. I create two tensors. I'm just doing this because I'm just making up two tensors here. I perform a matmul, then I perform a ReLU. I have two tensors, perform a matmul, perform a ReLU. So it's pretty easy to create a tool for this particular example to do the conversion. To save myself time, I just wrote this by hand. And also I wanted to make sure everything had good names. But tools like this exist, for example, Torch Dynamo, for example, TensorFlow's, I guess it's called the XLA tool. So there are different tools that do this. I just wrote this by hand. So this is what MLIR code looks like. Now, I want to be clear here. I have, if you go to demo2.mlir, you're going to find every single line of this commented in detail. So if I'm talking too fast or you want more information, go to that file, demo2.mlir, and you can get a full description of everything. But I'm going to walk through this demo line by line. I'm going to ignore this affine map for right now. It's used somewhere else. But the first thing I want to point out is this thing right here. This is the first occurrence of an operation. In MLIR, an operation is like a node in a graph, and I'll explain what that means in a moment. But this is an operation, this is an operation, this is an operation, this is an operation. An operation is really just anything that could take in any operands, produce any results, and it might have a scope, and it could have a name. And there's so many things that it can do. What it does is defined by the compiler engineer who made it. So, and every operation is part of a dialect. So now, normally for operations, you'll find the dialect comes first. So this is the func operation as part of the func dialect. This is the empty operation as part of the tensor dialect. But you may say, where is the dialect here? The module op is a very special op. Every single MLIR code, anything that's like .mlir, has to have a module op that surrounds it. It says anything in here is going to be compilable code. It's the highest level operation, and it's part of the built-in dialect. The built-in dialect is just used for organization within the infrastructure. These are dialects that the built-in dialect has nothing to do with the real code that's being emitted. It's mainly just useful for organization. So in this case, the module op just organizes that everything in this region is compilable code, and it might have attributes that apply to everything. For example, what device you're targeting would be an attribute of this module. And you'd find that as like a little string of JSON that you'd find right here. So every op can have operands, can have results. In this case, this op happens to have what's called a region. A region in MLIR is a list of ops. That's it. That's the only defined requirement for a region. It's a lot like a scope in C++. It just says that everything in here is an op in an ordered list. And what makes the module op special is that its region can only contain certain ops. So for example, the func op is allowed to be in here, but you can't put like an add instruction inside of a module op alone. It needs to have some, so there are certain, what defines those requirements comes from, again, the dialect itself. It comes from the compiler engineer that made this. So that's our very first op. Let's look at our next op. This is called the func op as part of the function dialect. Now, we've now hit our first real dialect. The built-in dialect is more just for organization. We're now in the function dialect. The function dialect contains ops, passes, or compiler optimizations, and anything that have to do with functional interfaces. For example, defining functions, calling functions. Anything you want to do with like a regular old coding function is abstracted into this dialect. So, and that's why the func op lives within the function dialect. And the function op can have a name. In this case, it's called main. This is the function name in C++. It can have some arguments. In this case, I don't have any arguments. And it can return a result. In this case, it's going to return a tensor as a result. A little brief aside. My original example, I didn't have a result. I had to add a result here just because in future demos, I'm going to do some optimizations. And the compiler was smart enough to notice that there was no result, so it just kind of optimized everything away. So it doesn't have to have a result. I just gave it a result in this case just for my future demos. Just thought I'd make that clear. And look, the function op can also have a scope. Scoped operations can have operations inside which have scope, which could have scope inside of them, and so on and so forth. There's nothing wrong with that. It's like a Russian doll of operations, where it's a hierarchical approach, where the module op contains ops, in this case a function op, which itself contains an ordered list of ops. Now, with the module op, if it contained multiple functions, it's not really order dependent. Here in the function dialect, they have made it very clear in their ODS, or the operation definition syntax, that these will be executed in order, because that matches what we'd expect from a functional coding style. Things will be executed in order. So now we're getting into these type of ops. These are the ops that are more like instructions that you'd find in C++. And these occur inside of a function operation. Before I move any further, how are people doing? Oh yeah, Andy, you have a question?
Yeah, can can you like elaborate more on what is part of the syntax versus what are like names that you're giving to things?
Oh, that's a great
So
question.
is func like part of the syntax? Does the function have to be called main? What are tensors? Like what defines what a tensor is?
Mhm. I'll get into tensors in a second. I'm glad you brought this up. That's going to be a pretty important part of this whole demo. But that's a really good question. Here's the thing about MLIR. It is super freeing to the compiler engineer to make whatever operation they want. So theoretically, the bare minimum for an operation is basically a space, a blank space. Now, granted, if you really want to do bare minimums, we have a function op. So this is part of the function declaration. Every function op will have, every single op has to have the actual function, like, I don't want to call it a function name, but it's the operation name. It's what does the operation look like when you code it? It's almost like the name you'd give a function. And the dialect is not required. I've actually had some fun. You don't need it, but sometimes it breaks if you don't do this. So putting func dot is kind of a requirement sometimes. But so for the function op, this is always going to be the same. And then this is always going to be the same. And then this is always going to be the same. Now, there's something that people get a little bit confused when they first start working with MLIR. They say, hey, why does the function op declare its return type with an arrow and other things like this do a colon? The reason why is because people are not consistent. The people who built MLIR, the people who make these different dialects are usually different people. And so so this is how freeing MLIR is. This arrow syntax is part of the definition of the function op. A person who defined the function dialect literally said, I want the result to be an arrow, and then the result comes next. So that's why the question of what is required, it's whatever the designer designed it to be. For the function op, it happens to be at sign and then the name of the function, open braces, the operands that will come in, close braces, space, arrow, space, and then the return type, and then curly braces. It didn't have to be. The person who built the dialect happened to choose this. But down here, they chose something else. So I hope that answers your question, Andrew.
Uh, so you're basically saying that nothing is required except
So
The func that func, like, what does that mean? Like, I
So
didn't get it.
let me actually go to the function dialect, the func dialect in MLIR, and just kind of show you, because I agree it is a little confusing. So if I look at these are all of the operations that are available within the function dialect. You'll notice all of these have a common theme. They're about functions. So I have a function call. I have a, don't worry about constant, but I have a function func, and then also the function return. These are things that you might want. And when I go down here, I'm looking for something in particular. Here it is. This is what the syntax looks like. And they didn't have it for func.func. I don't know why, but usually people write this down. And this is for specifically the return op, the requirements for what a person would need to write. It says that you need to write, don't worry about this really that much, func.return. That has to be there. Any attributes you have, this is like a JSON string, the open braces, the operands, and then colons with what are the type of those operands. And then this question
Mhm.
mark is optional. It means that this is optional. But this is specific to the func op, return op. If I go to any other operation, you're going to find that it actually ends up being different. So in reality, it's a little hard to say in general for all MLIR operations what's required. It gets all screwed up because it's whatever the compiler engineer forced it to be in the syntax. But generally speaking, people have come to the conclusion that good dialects tend to have the dialect dot, the operation name, and then usually they'll use braces, so for any operands coming in, and the return
Mhm.
type, whether they use arrows or colons is kind of random.
I see. So in this example, so func, tensor, arith, linalg, those are all dialects, right? And
I'll
then
get into that.
what comes after the dot is kind of like the operation. So func.func means like describing the functionality of an operation from the dialect func.
Correct.
And then I see. Okay.
Sadly, funk is a very bad example because this actually, some historical reasons. The funk op used to be part of the standard dialect, but they realized the standard dialect got so big that they started getting really annoyed. So they converted it into a funk dialect. They took all the arithmetic instructions, put that in the arith dialect, and they started moving everything around. So yeah, unfortunately, it's called funk.func, but you're right. So when you read an op, generally it'll be tensor dialects empty operation. If there's another dialect, it could be Alex dialect, alex.empty, for example.
Mhm. Got it. Okay. Thanks, Alex.
No worries. And then Vaughn also asked, is this part of the tensor dialect? So not all types have their own dialect. It just they don't have to have their own dialect. They just happen to. So for example, the tensor dialect does exist. I actually find that Google is the best way of going navigating these docs. And you can find all of the operations that you can find in the tensor dialect. But I'll get into that more in detail as I go through this example, because we're still not even done. We're not even past the third line. So what I have here is a tensor empty op. What does that mean? Well, maybe I don't know what that means. And I can just go into the tensor dialect and get a quick question of what does tensor empty mean? Empty tensor operations. You're going to find that the documentation, all this documentation is auto-generated. So it can be not so great at times. But it's an operation that defines a tensor of a particular shape. It can be dynamic, and the contents of the tensor are unspecified, and the only purpose of the op result is to materialize a specific shape in the IR. What does that mean? This is the equivalent of saying, I'm just allocating just random garbage. Now, granted, there's something very specific going on here. Now, what's going on here is that the return type of this operation is a tensor. In MLIR, a tensor is a clump of data. That's it. We have no idea where it's allocated, and hell, we don't even care what it's allocating, how it's allocated, how it's copied. We don't even think of it as allocated memory. We just think of it as a 256 by 512 by F32 values. That's all it is. We don't care how it was allocated at all. So that's what you should think about with tensors. Another thing about tensors that are different from other data types, which we'll talk about later, is that tensors are immutable. So I created a tensor called FC input. Because it's a tensor, it will never be modified. So at all points in this kernel, if you ever look at FC input, it will always be an uninitialized bunch of memory. That's all it is, or a bunch of data, I should say that. There's a difference between it and memory. So this will make more sense later. These I just made empty garbage just because they're supposed to act like my matrices. I could have passed these as arguments into the function. I chose not to because the syntax got a little gross, so I ignored that. But these are just, imagine I made a random input. Imagine I made a random weight matrix. This right here is the first instance of something called a value. Operations and values are the bread and butter of MLIR. Operations are that nested hierarchy of what instructions are going to occur when. The value, and they act almost like nodes in a graph. The values are edges. They say that the tensor empty op creates a value. This value is what's called SSA, or static single assignment. So FC input, you can think of it like a variable in C++, but you can never overwrite it. It was only defined once. It's static. It will never change its value. It will always be the same exact value, and it's only ever assigned once. That's what static single assignment is, and I'll explain why that's helpful in a moment. So I create another empty tensor, and then here's a new dialect, the Arith dialect. So the tensor dialect has a bunch of stuff dealing with tensors. The Arith dialect has a bunch of ops related to arithmetic. In this case, I just want to get a constant number. So I wanted a constant 0.0, and I'm storing that into a new value called cinit. And then what I'm going to do is pass that into another operation. This one's called tensor splat. And again, if you ever are confused, you can go into the tensor dialect and just kind of read up on what does tensor splat does. There it is. Broadcast the operand to all elements of the result tensor. The operand is required to be of integer, index, or float type. So great. It says fill that tensor, 256 by 1024, fill it with zeros. And so this is me just kind of initializing some tensors here. Next up, we have our first linear algebra operation. Now, the linalg dialect is filled with operations that will do linear algebra. It's a decent naming. So this case is I'm going to do a mapmul. It's going to take these inputs and this output. But I want you to notice something. I mentioned to you that the tensors are immutable. So why am I passing this one as an output? And then also, what's this FC output then? What is the difference between this output of the operation and this output, which is passed as an operand? This is specific to the linalg dialect. It works like this. When you perform a matrix multiply, you're going to be doing a bunch of multiply accumulates. There should have been data in the matrix before your output. Let me give you an even simpler example than mapmul. Imagine if I had a matrix of all zeros, and I had a linalg operation that only worked on the first half. It took all the elements and set them to 2. Well, then I need to know what was in the second half of the tensor in order for this operation to work properly. This is basically the initialization. What was in the output tensor before I performed the mapmul? And this is something that is necessary within MLIR. Now, you need to just specify that whatever was in there. In this case, for matrix multiply, because there's multiply accumulates in there, I have to initialize it all to 0. You'll see why when I start to lower this. But then for this later operation, which I'll get into, it looks very scary, but it's not that scary. I don't have to initialize it to anything. So I just give it a tensor empty, uninitialized input. You can think of this like an allocation. Yeah.
See, I'll define the dimension twice. It should be the exact similar as outside.
You're correct. This was just a design decision. I also had the same question. This acts a lot like the shape. They wanted to be, the people who created the linalg dialect know that a lot of people are extending the linalg dialect. It could be possible that you have multiple outputs. And maybe people do some strange stuff. Also, I'll explain this in a moment. This is optional in the linalg dialect because once we lower the abstraction level, I will need to actually use the outs properly. I'll explain what happens later. It gets a little weird. So all this is saying at a high level, I have my FC input matrix, I have my FC weight, and I have whatever the initial value is for my output, perform the matrix multiply, and then return it in FC out. Next, I need to do my ReLU. Now, MLIR, if I go to the linalg dialect, sure.
This is just the way the linalg people decided to do it.
Yes.
The syntax is like, seems slightly different.
It's yes.
Like, so their ins is they just have this macro that they put around their inputs, I guess, or is that part of basic
So
MLIR?
again, with MLIR, it's super freeing that allows the compiler engineer to do whatever they want. FC input, FC weight, and matmul init are all operands. They're just inputs. I could have.
Those are my real inputs. I'm talking about the actual word ins and brackets.
Yep.
Is that just linalg decided we'll wrap all our inputs in some little macro called ins?
Yep. It's not even a macro. I don't even want to call it a
So it's like
macro.
a little thing that just tells me they're ins.
Yes.
Syntactic, which
It is just syntactic sugar. It's just saying for the user, these are the ins.
okay, and then another one called outs,
Mhm.
and then they define the type of the return. They're
Yep.
defined in a slightly different spot. They define it kind of at the end, whereas like the funk dialect kind of defined it at the beginning, and I guess that's just
So it depends on how you see it. This is, yeah, you're right. Even down here, they put it at the end. Again, consistency in MLIR is a little strange because so many people work on it.
So just don't worry about that. That's just the way they did it.
Yes.
And I mean, I have seen some people whose coding convention, even as they actually, Jason Liu used to do this, he used to literally put a macro that resolved to nothing in C++ code that was ins and outs. And he'd wrap it around variables in C++ code to tell you this is an input, it's an output. Like I know this is like syntactically, they just decided I'll just put ins on some things and outs on some things, but only linalg did that, or maybe a few other.
This is the only dialect I'm aware of in core. Now, there are dialects that are outside of the core dialects that are not in MLIR upstream. For example, I think the Tosa dialect also does this, as well as some higher level dialects.
Okay, and then the outs, I know you described this, but I don't know if I fully understand.
It's-
So it has an output, which is FC output, and that's done through the assignment operator like usual. But it also has an out called matmult init. And the matmult init, I guess, is because you're doing matmults. What is this? I mean,
I'll
basically, setting up the tensor where the results will go, and
So-
I basically have that.
I'll explain this further in a moment, but in the tensor level of abstraction, the output of a tensor, the tensors are immutable.
Yeah.
So the only way I can initialize it with some value is to tell the linalg dialect, here's the initial values. And then once it writes to the output, it's aware of what the initial values were. Now, when I lower the abstraction,
I think this is the definition of this basically overwrite those initial values. And
Well,
just getting the shape from it.
so in this case for matmul, it depends on the lowering. In this case, the lowering for matmul actually does rely on the inputs because
It just adds it in and treats it as a matrix multiply accumulate.
yes, this is more like a matrix multiply accumulate. I think that's a bug,
In which
actually.
case, that's kind of an in-out, so it's used as both an input and output.
No, it's not an in-out. I should be clear because we're not modifying this tensor. Matmul init does not get modified. It can't. No, the reason why they call it an outs, I was going to save this for later, is because when I lower this to the to the memref dialect, there's no return type here anymore. This is because the output can actually be modified in place.
Yeah.
It's a very interesting design choice. I think they should have done a different dialect, but they chose to do it this way.
Is there a rule of why they have to call that, like, is there a short rule of why I have to call that an out?
No.
In linalg versus an in, because you're saying it is also an input.
It's the outs provides the shape and the initial value for the output. So they chose to call it outs. In reality, all three of these are inputs. So these are, this is a completely different value.
Right.
It could have the same value, whatever init was. It might not, most likely won't.
No, I mean, it's like, it is the real output, right?
Yeah, that's the real output.
The matmult init is not actually changed.
No, it can't be changed. Tensors are immutable.
Yeah, I guess I'm just, maybe I'm, right, I'm just wondering why they called it outs then instead of just other input.
I've asked myself the same question. I'm not sure. It's really because I think it's because they want to differentiate what are the true immutable inputs and what are the output or things that are pertaining to the output. And in this case, it helps with the shape. Yes, Andrew.
What happens if I mess up the dimensions?
Oh, it crashed.
Does-
I'll show you what happens actually. I can actually do that as a real demo. I'll do that in a second.
Okay.
Actually, you know what? Because you asked, we'll do it. Let me go to build. Oops, not build.
You don't have to go out of order. Like you
I don't
can keep
mind.
going.
It's totally okay. So demo 2, this is the exact, like as I told you, I put a lot of comments in here so that people can use it. And what Andrew asked is, why don't I just make a mistake? Let's make this F16. I made it F32 before and I changed it to F16. What I'm going to do is get my build bin MLIR OPT. I'll explain what this tool means in a moment. But what it allows us to do is it will basically proofread our code and tell us if there's any syntax errors. So our compiler engineers said that those two types need to be exactly the same. And because I made a mistake, it tells me use of value matmul init expects a different type than prior uses. Oh, that's a different error. Whoops. So this is not what you asked. That's because this init is also F16, and this one's going to be F16. I just want to be absolutely fair. Yep, and this is what I was expecting. Oh, wow. It really gets all angry. So linalg matmul expects an operand of type operand 2 to match the corresponding result. So it actually will catch you. It's pretty great. I'm going to go
Okay.
through,
Okay.
this is actually perfect timing for this. So this is MLIR OPT. It's the optimizer in MLIR. It is a debug tool. People do not use this as part of their real compiler because what it does is it takes in your MLIR code, checks it for syntax errors, and then writes it out. Or if you tell it to, you can ask it to do compilation passes, and I'll show you that in the next demo. And it will do those optimizations, but every optimization, it will run the syntax checker every single time. So if you do this as part of your real compiler, it will be very expensive. So normally people make their own tools, which will call the passes under the hood. So that's MLIR OPT. It's actually a really great tool. I'm actually going to fix this because I actually do want to show this actually working. So don't mind me. But yeah, if you have any questions, like if you want more details on everything I'm saying, everything is found within this file right here. And this is the last one. Let me just check to make sure I didn't make a mistake. Yep. It will actually write out the code if it's happy. And in this case, it also changes all the variable names. So it also cleans up the code quite a bit. So I'm going to quickly finish this demo. So the linalg dialect, it's one of the biggest dialects in MLIR. It doesn't have a ReLU operation, but I need to perform ReLU. So what do I do? Well, linalg provides a generic op. The generic op is a way of creating a linear algebra operation in general, where you, the user, can define what does this arithmetic, what does this linalg dialect, what does this linalg op do? So my ReLU op takes a input, which is the output of the matmul. It produces something of this shape. And in this case, I don't care what it was initialized to, because my ReLU will either set it to 0 or whatever the value was. So that's going to be a tensor empty. And it's going to return a tensor of size 256 by 1024. It's the same size as my input. And these indexing maps in iterator types is basically telling us when I'm performing my linear algebra on this input, how am I going to index into it? Well, it's a standard, this is the identity index. This is in case you wanted to do transposition while you're indexing. And down here, it's saying, when you're iterating, how should I interpret this? Well, each iteration while you're performing the ReLU does not depend on any other, so it's parallel. This is actually really challenging, so I'm going to skip this for now. I know probably have questions on what this means. It's actually quite more complicated, so I'm not going to get too in depth on that. But down here is how the user will specify what happens on each element of the ReLU. And in this case, what we're going to do is I'm going to use my arith constant again to create a constant 0. I'm going to compare with the input, which is right here, and %sign z0 and get a comparison. I'm going to select based on that, and I'm going to yield the selected result. This is just ReLU. And you'll notice that I pass in the input and the output. This is what was in the init matrix originally. This is why we have to specify what's in there, because if not, maybe I need to use percent sign out. Now, as you can see in this kernel, I never use percent sign out. That's why I'm allowed to use tensor empty here. But if you look at how matmul gets lowered, it actually does use percent sign out. So therefore, it actually needs the init to be set to something like 0. Yes.
So just to be clear, what linalg matmul is doing is it's multiplying FC input by FC weight and then plus matmul init.
Really, yes. It's a little. I actually originally made a mistake in this code when I first wrote it. I originally made this tensor empty and I got the wrong result. So I actually set it to 0 after the fact. It is a poorly named function, in my opinion. So now, and then we've returned the output. This is part of the function dialect. Now, I was super adamant that tensors are immutable and they're SSA. What's the benefit of doing that? Well, the reason why this is so great. Oh, yes, Andrew.
What is BB0 and UGT?
Is this part of the specification? This actually goes back all the way to LLVM. This is defining what's called a basic block. In MLIR, remember how I said these regions are lists of operations? I lied. I wanted to make that a little simpler for you guys. These regions are actually lists of what's called basic blocks. Now, the module op and the function op both have a single region with a single block in it. So it makes it a little cleaner by ignoring it. Here in the linalg dialect, they chose to actually name the basic block. So this is called BB0. This is the name of the basic block. It could be anything.
Call it like hat BB0.
Yep, it's hat BB1, hat BB2, hat BB.
Hat is not special. Just chose that or what?
No, that actually is. I don't know. I think you have to use the hat.
Okay.
It's just, this is what's called a basic block. It comes all the way back from compilers back in LLVM-IR. And probably not today, but next week, I'll show you guys what this looks like in LLVM-IR, and it'll make a little bit more sense. But the idea is that basic blocks are places where you can branch to. You can branch to the start of this basic block, and the ending of every basic block needs to be branching somewhere else. Here they cheated a little bit. The linalg yield actually becomes a branch eventually. It gets a little nutty. This is probably the worst part of the linalg dialect, in my opinion. Having these basic blocks inline like this, I think it's because people got a little. There are ways of making this cleaner. I think they just have never cleaned it up. It's the classic compiler engineers. It works for them, so they're not going to fix it for other people. It's a great
So
question.
this is a unique identifier. So any basic block I define have to have a unique name.
Yes. And
Okay.
yes, it's
And then the UGT is like, I assume something like unsigned greater than.
it's actually not unsigned. It's a little bit weirder. There's OGT and UGT. It's ordered and unordered. Compiler engineers. There is like how you handle infinity and how you handle some of those exceptions changes which operation you use. It's all explained in
I
the
see.
documentation.
Okay.
The other question on this, okay, so linalg generic expects you to send in like an input and output. Your output is really not really an output, it's really like a shape and an initialization.
Yes, it's exactly that. It's a shape and initialization.
For inexplicable reasons, they call it wrapping the out. And it also expects some mapping functions, which I don't fully understand yet, and it expects a basic block. Is
Yes.
that correct? Or an operator, which could be a basic block. I guess it could have been maybe a predefined operator.
This has to be a basic block.
That has
If you go to the
basic
linalg,
block that you write, but I guess maybe linalg generic just says it must be a basic block.
yes, it is just that's just how it is. Generic. There we go. It does basically just say they call it a region, but they do basically just say. Yeah, I wish I could tell you guys more about this. It is. Oh, and I guess now is a good time to maybe explain this a little bit. So remember how I said,
So it's going to apply that basic block on every element in your input.
correct.
According to that mapping function.
Yes, and it is according to the mapping function.
So entirely understand why two mapping.
Yeah, so we have the indexing maps, which will tell you, in this case, we have a 3D input.
Okay.
Let me check. No. it's a little bit more complicated than
In your
that.
example, you had two maps.
Yeah, so
Those
this
two
gets,
maps.
matmols are really expensive, are really complicated.
Okay.
I'll talk about this more when I start doing the lowering. It'll make more sense if I show the lowering. Ignore it for now.
Uh, okay.
That's probably one of the hardest parts of
And
the
you're
linalg
referring
demo.
back to your map at the top, define the map function at the top.
Yeah, I could have just inlined this. I could have done
So
this.
that's,
This is more like a macro.
is that like, is that a standard MLIR as well? Like hash means macro essentially?
Pretty much.
Okay.
It's
so
actually not
I'm
called
gonna
macro.
Find a keyword that I'm gonna find whatever you want to call it, not a macro, something.
I don't know what it's called, I
But it's
forget.
basically a textual substitution.
Yes.
Finding an identifier and you will just, so that's basically a find map.
Yeah.
It's getting pasted in there.
Yeah.
And there's two of them, I don't know why, just take your word. Okay.
So it's because we have two dimensions and we're going over those two dimensions. That's why.
Oh, your map is actually mapping two dimensions to two dimensions as well.
My map, yeah, no, this is actually, how do I explain this? Sorry,
I mean, I'll stop.
I think I got unlucky.
So,
The indexing maps are how do I index the first input and how do I index the output? That's what these are. And this is how
let's say just use transformation.
yep. And then the iterator types is saying, how will you iterate over each of those dimensions? The first dimension I'll do in parallel, the second dimension I'll do in parallel.
Okay, so you're saying linalg generic takes, in this case, took one input, one output, the output's kind of an input. And so you have to give it two mapping functions, which in your case, because it's 2D tensor, they're mapping two indices to two indices.
Correct.
Okay, great.
Fun stuff. So because I was so careful with making these tensors immutable and SSA, we can actually represent our, there we go. We can represent our data as a DFG or a data flow graph, where every operation is a node in the graph and every edge is a value. In this case, it doesn't have to be a tensor, but because these tensors are immutable, it's very easy to analyze this. Because I notice that, hey, look, I have my linalg matmul that produces a result, and that result is immediately fed into the linalg generic and never used anywhere else. And I can prove it because there's no pointers. So I know exactly that this tensor is only ever used in this case, never used anywhere else. And I can realize that, hey, maybe if I have a special architecture that can do both matmul and ReLU at the same time, maybe you have a special FPGA that happens to have that op built in, these can be fused at this level of the kernel. Now, if I was working with lower level for loops and stuff, that would be very challenging. That would be actually really, really challenging to do that kind of fusion. But here, at this high of a level, it's really easy to tell that. And so that's one of the main benefits of using SSA form and one of the main benefits of using SSA values that are immutable. Now, it is currently 4:58. There is no hope in me getting to demo 3, but I think I will spend the last 2 minutes just trying to answer Vaughn's question, just so that I can like have some restful sleep tonight. So if I go down to how this, oh no. So when I lower this into, is this the right one? When I lowered that linalg generic, it gets lowered into 2 for loops. The iterator mapping defined these loads and stores in here. This load is the first mapping, which says that when I index into this, index ij, and when I read to the output, I use I and j.
This would allow you to do things like transposes and so on if you want.
Correct. And then finally, when I put those parallels in there, I'm saying that I'm going to be building this out of 2 for loops that each iteration does not depend on the prior ones. Now, other values you could have given this is reduction. Maybe you needed to reduce along one dimension. So that's why you have to specify them every time. Now, in my opinion, I would have just not specified this. In this example, it actually makes it so complicated. This is basically just the most basic bread and butter one you could do. So in my opinion, this should just be blank and the default should be this. But because MLIR wants to be very explicit, they make you have to explain it this way. So I have to be explicit here. So it's a bit over the top for this demo, in my opinion. So there's no, oh yes, Andrew.
So let's say I write this code and I I don't know what the right term is. I compile it, right, into this data flow graph. So now this data flow graph is stored in some sort of an internal data structure that I can traverse and basically calculate statistics on or something like that.
It's
Like
even easier
how
than
does it
that.
work?
The way that MLIR, now this is beyond the scope of this tutorial. I'm trying to keep this at the IR level, but in the MLIR's infrastructure, MLIR actually stores this as a graph. This entire IR that we're looking at here is stored as a control flow graph. So operations calling other operations, which call other operations. This nesting that you,
There are walkers to just go.
yeah, there are walkers in there that allow you to walk that graph, exactly, and do analysis and stuff like that. So for example, this
I
FC
see.
input, it's a value, I can ask who defined you. And I can ask that FC input, where are you being used? Which operations are using you? Stuff like that. And then there are walkers that exist to say, okay, give me the module op. Tell me who's inside. Ah, the function op's inside. Tell me who's inside it. And then you keep going down the chain. That's what the walkers do.
I think the only
Nice.
syntax in this example is defined by MLIR, not by a dialect, is like the hashtag syntax for a keyword substitution.
Correct.
Or a macro substitution, the module itself.
Which is part of the built-in dialect, but it's,
All that.
yeah.
I think that's kind of it.
Yep.
And I guess all variables have to start with percent, is that correct?
Yep, all variables or all values need to start with percent.
Values need to start with percent, and other than that, everything's defined by the dialect.
Yep.
Is that right?
And that's by
That
design.
explain my part of why guys have been reading this stuff and going, I figure out the rules, because I guess they're not that complicated.
They're not.
Okay.
The thing is, MLIR by design made the dialect freeing to the compiler engineer to build whatever dialect they need, whatever representation they need. People have converged on common practices like this tensor.empty, putting dialect dot the variable, the value name. That used to not be required. I think it might be required now. The last time I tried not doing that, it crashed in random places, but only later. So it's confusing.
Find maps also are the built-ins then, or what?
No, a find map. Oh, yes, it's part of the built-in dialect. I think. The affine map's confusing. The affine dialect gets very confusing. That's my fourth demo.
But I don't know, given the syntax, it doesn't even look like it's part of the affine dialect because it doesn't have the dot notation.
Yeah, that's why I think it might be the built-in dialect. So yeah, welcome to MLIR. So this is one of my favorite quotes from MLIR. I heard this from a professor from a conference that we were talking at. He said that MLIR is the best compiler framework because it can do anything you want. Then you ask the question, can it do this? And they say, no, but you can make it. So that's my favorite thing about MLIR. So anyways, thank you guys so much for listening, and I will definitely see you guys next week.